Okay, for this part, we are looking at the ways that lines can intersect or interact with one another. What I'd like you to do is try graphing these by hand, A, B, and C, and figure out what the solution is for each one. And then if you're stuck or when you're finished and want to check, I will go through the explanation of these. But try it on your own first, and then you can check your answers. Okay, when I graph these lines, the very first one, y equals 2x minus 4, I used my slope y-intercept method, and I plotted the minus 4 on the y-axis, and then I used my slope to rise and run to find other points on that line. For the second equation, it's more like standard form. It's not exactly standard form, but it's more like it. So I found my x-intercept by letting y equal 0, and I found it was going to cross the x-axis at 4. That should have been in red. And then I found my y-intercept by letting x equal 0, and I found that that also crossed at 4, which gave me 2 distinct lines and 1 intersection point. It's not a very easy intersection point to read. You could check it on Desmos, but it looks approximately somewhere like 2 point something and comma 1 point something there. Maybe, yeah, like a 2.8 and a 1.8 or something like that. But check it on Desmos. That is one of the downfalls of solving by graphing when you don't have technology to verify your solutions. Part B, I, again, for the first line, used the slope and the y-intercept to get my y-intercept at -7 and my slope to be a +2. The second equation, I decided to rearrange that into y equals mx plus b form and then use slope and y-intercept. I could have worked with x and y-intercepts, except then I would have had a fraction, because for the x-intercept I would have had x being 21/6, which then could reduce to 7/3. But it's not the easiest to graph that way. So I thought I would rearrange that one. And what interestingly happened is I ended up with my line having the same equation as my other line, which meant my two lines are crossing on top, or sitting on top of each other. So they're crossing at every single point. Those two lines intersect at an infinite number of points. So it is possible for a system to have an infinite number of solutions like part B. So part A had exactly one solution, one intersection point, one solution. This had an infinite number of solutions. Because the two lines lied on top of each other, so every point on the line was an intersection point. And what we can write that one as, we don't say a specific value for x. We can say x, the x coordinate of our intersection point will be anything. It's going to be x, where x can be any real number. And the y coordinate is defined by the equation. The y is equal to 2x take away 7. So whatever I choose my x value here to be, I'm going to replace that x in this little expression, 2x take away 7, and that becomes the y coordinate that matches it. So that's how we express our solution when there's an infinite number of solutions. All right, looking at the third example here, part C, I used slope y-intercept, and then I used my x and y-intercepts for my second equation, and I got two lines that graphed as parallel lines. And we know that parallel lines, they both had a slope of 2. Parallel lines will never intersect one another, so this is a case where we have no solution. There will never be an intersection point. There's no solution to this particular system. So there's really 3 outcomes that can happen. You can have one intersection point, you can have an infinite number of intersection points, or you can have no intersection point at all. So on the next page, we are going to summarize that. So types of lines, we could have intersecting lines, there we go. And you could just do a quick sketch of a graph of lines that intersect one another at a single point. So set up a set of axes, an x and a y, and then you can draw 2 lines Doesn't matter what those two lines have as slopes or y-intercepts. The key is, they can even run the same direction. The key is those are going to end up intersecting at one single intersection point. With these lines, to be able to intersect at a single point, these slopes have to be different. They can both be positive, they could both be negative, but the key is the slopes have to be different from one another. If they weren't different, we either have parallel lines that are distinct, two separate parallel lines, or we have parallel lines that are coincident. Coincident means they lie on top of each other. So slopes here must be different. Must be different. There we go. I think that fits in there. Must be different. Our y-intercepts, who cares? They could be the same. If they are the same, then that happens to be the intersection point. But they could be different. Might be the same or might be different. There really is no requirement there. Might be the same, and that means it's the solution, or might be different. See if I can get that to fit a little bit better here. Might be the same or might be different. In this case, the number of solutions is that there is exactly one solution here. And there is a fancy name for this. I'm not going to test you on this. I don't believe that you really need to know this, but this kind of a system is called a consistent independent system. Okay, consistent independent system. We don't, as I said, I don't test that. I'd rather you know that those two lines intersect each other. All right, the second set here that we're going to put in are the case where we had the parallel but distinct lines. Parallel and distinct. Distinct means different. Okay, different from something else. So parallel and distinct lines. A little sketch of that. Draw your axes. X and Y. And then draw a couple of lines, and you want to make them run in the same direction but be different. Okay, not lying on top of each other. So parallel and distinct, these have no solution. Okay, number of solutions, there's none. There's no solution. With these, the slopes must be the same to have the same direction. Slopes must be the same. And your y-intercepts have to be different, because if the y-intercepts were the same, they would lie on top of each other. So these must be different. So these are things that we're going to check when we are looking ahead at equations of lines and trying to predict what's going to happen there. This is called an inconsistent solution, or an inconsistent system. And again, I won't be testing you on this. I don't think these fancy names are important, but knowing the three ways and the three scenarios is important. All right, the last part are ones that we call coincident. So that means our lines are parallel, but they lie on top of each other this time. So this is where it's good if you do have your multiple colors that I requested that you bring to class. I'm going to draw my one line, and then I'm going to draw another line in a separate color and make it look like it's lying over top of it. So I'm showing the two different arrows, the blue and the red show up, but it looks like my two lines cover the same space. All right, so in this case, our slopes must be the same so that they can go in the same direction. And then along with that, our y-intercepts must be the same, because that way they are exactly the same line. Okay, and this has an infinite number of solutions here. These are eyes here, infinite. Okay, and the fancy name for this one is a consistent dependent system. There we are. Okay, your job for question 2 is to determine the number of solutions that each system is going to have, whether it's going to have no solution, one solution, or an infinite number of solutions, without solving it. Don't put it into Desmos. Don't try and solve it algebraically, but explain how you know. So the key ideas here are that you need to really examine what your values for your slope are and your values of your y-intercept are. So the very first one, if I'm looking at that one, take a moment, figure out your slopes. Are they the same or are they different? If they're different, then right away you know it's case number 1 where you have one intersection point. If they're the same, then you need to look at the y-intercepts. So first step, look at slope. Second step, if need be, if the slopes are the same, then look at your y-intercepts. Okay, take some time now to look at question 2 and I'll put up solutions.